So my name is Amit Kohn, and actually, technically, I shouldn't be at this workshop because my current workplace is at the Department of Materials Engineering at Ben-Gurion University. But as of last week, I'm transferring to the new department here from October, so that got me into this workshop and also landed me this job of being the session chair. So
it's only a start.
In October.
It's only a start.
It's only
when the things come.
Okay. So so in this session, I think we have quite a range of topics. In fact, the third one is a mystery. There's no title for the talk. So I think I'll just start for myself, and if anyone could just give me the time, or if you run outside, I don't know. I should end. Okay. So I gave this talk, a rather general title, about chemical ordering and operation of a rather specific device, a magnetic tunnel junction. First, I'd like to say that as a research theme for myself, I work on mostly magnetic materials and semiconductors, electronic materials, in devices typically used for information storage. And I do a kind of structure property relations kind of work, where the main experimental methodology that I use is related to transmission electron microscopy in a range from analytical all the way to Lorentz TEM for magnetic imaging. So actually this talk is also an opportunity for the many colleagues from Tel Aviv I see here today that I can also describe a bit of what I would like to do here as well. So I'll be talking about a specific magnetic device, but actually another topic I work on is on holography as a method of mapping electrostatic and magnetic fields. And this might already be known from yesterday from David's talk, that he was checking with a 3D atom probe silicon nanowire that's sort of vertically p-n doped by Roy Yerushalmi from the Hebrew University. Well, you have to give great credit to Roy that he tries every possible methodology to check his p-n silicon wires. And in addition to the atom probe and to STM, this is a method done in the TEM by electron holography. And basically what it does, it maps the electrostatic potential in your material. And in the case of a semiconductor, the variations in potential basically follow the band structure. So if you have something like silicon, and this color code is just to show the change of the potential along a scale of about 1 volt. That's just the gap of silicon. It's quite highly doped, what Roy is doing. So you can see a proof of the kind of doping he was more or less aiming for, sort of vertical doping. But the same approach can be done for magnetic components. So through the electron holography, you can map the magnetic induction. In this case, this is a circular nickel-iron element. And what you see in this kind of representation is sort of an equiphase representation. It just tells you the magnetic induction follows these equiphase lines, and the magnitude of the potential of the magnetic induction is basically just the spacing perpendicular. So it's like a topographic map, you can think of it. But anyway, you can see a flux closure here. So these are the topics I'm working on in terms of methodology and application to electronic materials. This time, I just wanted to choose a device, a rather important device from a technological point of view, which is the magnetic tunnel junction. I'm just showing here the heart of it, along with the kind of typical materials you might find in technological applications. And the idea is that you have two ferromagnetic electrodes separated by a thin 1 to 3 nanometer thick barrier. Today it's magnesium oxide, epitaxial magnesium oxide. And what you do is you follow the tunneling sort of through the barrier, so the current perpendicular to these electrodes. And it turns out that if you take care of the structural details, you can get a very strong spin-dependent tunneling effect. In other words, when the magnetic moments are parallel, the probability of tunneling is high, and therefore the resistance of the device is low. And when they're anti-parallel, the other way round. And in addition, if you want to use it as a sensor, which is what those of you who have a hard disk drive, this is the sensor device, you need one of the electrodes to be fixed in its orientation with the magnetic moment. And this is done by another phenomenon called exchange bias. This is a sort of typical material used. So the device works in this range here. You see resistance as a function of applied field. In terms of sensor, what you really need to do is you need to have a perpendicular orientation of the preferred alignment of the magnetic moment, so that when the sense layer, when it rotates like a spring, so you have a linear response rather than this hysteresis type response shown here. And if you apply a large enough field, then of course you can reverse also the magnetic moment in the pinned layer, but all the sensors work in this range. And there's also, for quite a number of years now, an attempt to use this device as a memory element. There are a few technological products, but it's nowhere as successful as for sensors. So this is the idea. And the choice of epitaxial magnesium oxide is not coincidental. It functions as a spin filter. It turns out that due to symmetry matching between the magnesium oxide and the ferromagnetic electrode, there are certain block states it allows to transmit, certain ones it doesn't allow. So this enhances very significantly this effect, which can be, the change in resistance can be many hundreds of percent, even in some cases 1,000%, a very, very strong effect, significantly stronger than the GMR effect, giant magnetoresistance, that at the time that received the Nobel Prize in 2007. So this is where it's basically used in the hard disk drive, and just to show the technological importance of it. So most digital information used today is still stored by magnetic materials. Here's the sort of scale of bytes being shipped per year. You have to count it today in exabytes, which are billions of gigabytes, or maybe you need to go to zettabytes today. And the device I was describing just sits here. This is the read head, the sensor. And here's a comparison, the comparable Moore graph, Gordon-Moore's law, for magnetic materials. So here you see the production year and the areal density on your hard disk drive and how it keeps growing. And just to see the competition of the various solid-state type memories. But this is actually a more interesting graph than Moore's law, because you see it's a logarithmic representation, and still you have changes in rate. And these changes in rate are related to the introduction of new types of devices and technology, like the GMR and the TMR head. I thought it just interesting to give you a scale. There was an attempt a few years ago to try and estimate how much information there is in the world. And it's not an easy task. And there was no claim about the importance of the information. Most of the information is garbage. But anyway, here's an estimate of from the mid-'80s until today. Look at the growth from an exabyte, as I was saying, is 1 billion gigabytes. From a few exabytes to thousands of exabytes today, and it's growing exponentially. And all of it today is digital. So those of us that used stored information in the 80s, it was by various, non-digital methods, which doesn't exist today. Today, it's pretty much everything's digital. And so are we at the end of it? Is there still a potential to store more information? Well, in fact, all this amount of information is about the amount that each of us stores. So if you think about the amount of information in one body in the DNA, it comes up to about a few thousand exabytes. So I think we're just at the start of it in terms of the amount of information that needs to be stored. So anyway, this is the device, and it's actually very rich in materials engineering, materials science questions. So here's a few of the questions I've been looking at recently. Of course, I don't have the time to present all of them, but just to give an idea. So for example, the issue of the type of the ferromagnet electrode. You know, if you could find a material which is half metallic, in other words, it's fully polarized, all the electrons have the same type of spin, then by definition you're going to have a very strong tunneling magnetoresistance effect. Currently what is used are based on transition metals, which have a polarization of maybe 40 to 50%, 40+%, and this limits the ultimate sensitivity of this device. If you could find a material which is fully polarized, and one such candidate is from the Heusel family, it's cobalt-2 manganese silicon, that could be interesting. So that's one topic we've been looking at. Now, I've been showing you these magnetic moments which are parallel to the thin film structure. But in fact, in the last, say, 2-3 years, the media in the hard disk drive has moved to a situation where it's perpendicular. The magnetic moments are perpendicular to the thin film or to the platter of the hard disk drive. And this is in order to combat issues of thermal stability. It's done by using very high magnetocrystalline anisotropy, and of course to get higher areal density. So actually new sensors have to look for electrodes where the magnetic moments are also perpendicular. And one such potential material is iron platinum. It's L10 ordered, not a simple alloy. So that's another topic. Another issue we've been working on recently is the application of this device as a memory element. And the problem, one of the problems for this memory element is the fact that the magnesium oxide has actually a very large band gap. It's quite strongly insulating. So you need quite large currents to run it as a device, especially if you want to use currents in order to switch magnetic moments through spin torque effects. So we've been looking at an option of doping the magnesium oxide with zinc. When I say doping, it's actually quite a large amount of zinc, up to 0.3 fraction of in this material. And what we want to achieve by that is to retain all the properties in principle, the same structure, but reduce very significantly the band gap, so increase the currents. So that's work done on the tunneling barrier. And I've had a very long-standing project on the phenomenon of exchange bias with exactly the material which is used in industry, is iridium manganese 3. So this is just late reports, but this has been going on for quite a number of years now. So I don't know how time-wise, I'll start off with the Heusler, and what I want to show there is some of the capabilities that TEM structural characterization can give you. So here's the material that's being suggested for the ferromagnetic electrode, and it has all sorts of crystallographic options, which are basically the degree of chemical ordering, from full ordering, which is the L21 structure, to complete disorder, which is the A2, and you can have all sorts of defects in this structure. But anyway, for the L21 and the B2, those people who do first principle calculations, then they predict that this is going to be a half metallic material. So you can see a relatively reasonable band gap for one spin state, and it's metallic for the other case. That's not the situation for A2. So if you could achieve, in principle, this kind of structure in the electrode, then you can expect full spin polarization and a very strong effect in the device. So this has been work that we did in collaboration with a group at Tel Aviv University, and they grew these thin films based on sputtering, which is sort of more industrially related methodology, and they achieved an epitaxial growth with the following epitaxial relation, and the overall composition is okay. And basically, we wanted to influence chemical ordering by the degree of post-growth annealing. So we had a certain range of annealing, and these are also annealing temperatures which are in the range which can be considered for the application, the fabrication of the device. So this is what we got. We got a fairly typical result of what you can find in the literature. So even though it's predicted to be fully spin polarized, best cases in a magnetic tunnel junction device, which is what we checked, you can find maybe up to 60%. And this is what we saw, spin polarization as you start off very low, and then it sort of goes up, peaks at around 400 degrees centigrade, values that are, they're better, but not significantly better than transition metals, and then they drop down again. And the question is why? Okay, so this is the prediction. This is the kind of polarization people report in these devices. So it's back to the theory people, to try and explain. And there are all sorts of explanations that have come up for this sort of phenomenon. So the obvious one has to do with chemical disorder, especially the A2 disorder, the cobalt antisites. The structure and composition of the interface layer has turned out to be very important. It turns out that it has to be a manganese terminating layer. And other potential possibilities have been raised as basically an interaction between the ferromagnetic electrode and the magnesium oxide tunneling barrier. So these are exactly the questions that we were looking for. The chemical disorder, especially at regions of the interface, the structure and the composition of the interface layer. So this is where the TM can really help. There are a lot of questions today that have to do about the interface structure and the terminating layer, very critical in terms of the operation of the device. And obviously intermixing or out diffusion. So actually when we look at these various electrodes, we see an improvement or an increase in the degree of chemical ordering from as deposited to the high thermal annealing. And we can also map it, this degree of ordering, say from these phase contrast, high resolution TEM, we can filter out the 111 reflections, which are a signature of these L21 chemical ordering, and basically locate the position and just find that this phase nucleates homogeneously throughout the layer. We can quantify it and compare it to X-ray diffraction, to rocking curve type measurements. There's a good fit between the two. And actually what we see is just an ongoing improvement. And when you combine it also with magnetic measurements, you can really map the various phases from the L21 to amorphous as a function of annealing. And really what we see is that the material should be just fine, because at the high annealing temperature, there's a large component above 80%, which should be half metallic, and it's evenly distributed also at the interface. But obviously that's not the whole story. So there must be something related also to the structure and composition of the interface. And this is where these new microscopes are playing an important role. So this is a Z contrast, high-angle annular dark field image using an aberration-corrected microscope. And the nice thing about this type of imaging, it's very strongly correlated to the atomic number. So it's a Rutherford-type scattering, and it has very high resolution. So basically, you can pretty much read directly from the contrast here what type of atoms do you have, cobalt, manganese, silicon, magnesium oxide, and so on. So here's an example of just a certain region, just in a color code, the measurement and the simulation for the certain L21 structure. So that's okay to look at the material, but what's really interesting is to determine what's going on at the interface, what's the terminating layer, and what the structure is there. So this is what you can do. You can go to the interface and just look at the intensities from this type of measurement and relate it to the type of atom. So this is the interface. You can see it's, or you can determine it's cobalt, and then actually the terminating layer is manganese silicon, and then you start off with magnesium oxide. But thanks to image simulation, you can take it a step further, and you can really check the exact intensities between the simulation and experiment, and fine-tune it to really determine the composition. So by doing these comparisons, we could determine that this interface layer is also partially oxidized. So the terminating layer is basically manganese silicon, and there's also oxygen there, either by steps of the interface or partial oxidation. So this actually turned out to be an interesting result in the sense that it fits the the predictions from calculations. So this is the stable termination layer. Unfortunately, it also creates surface states. So, and this turns out to be quite critical in reducing spin polarization. So since there's been work done on trying to force the interface to be manganese rich, which actually keeps, 5 more minutes, keeps the polarization. Okay, and finally, in this case, for out diffusion, so here's a case where you can map through electron energy loss spectroscopy the various composition from the layer into the, in this case, magnesium oxide substrate. And we could see that there's an out diffusion and accumulation of manganese in the layer, in the barrier itself. So that's another component. So basically, if we summarize just very briefly, the material should be fully spin polarized. And in terms of chemical ordering, the structure, it just goes up. So we should have expected this kind of result, just an increase in polarization as a function of the annealing processing, the temperature. But we see that there's diffusion of manganese into the magnesium oxide. So this changes the compositions, changes the tunneling properties. And finally, the issue of the terminating layer reduces the overall maximum spin polarization that can be achieved. So these are the 3 phenomena that we want to explain this result that we measured, and is actually very typical for devices that are reported in general. Okay, so I've just, just a few more minutes. So here's another topic that we looked at, is exchange bias. I don't really have the time to look into this. I just want to give the bottom line here. This is the material which is used in all these devices, and we're talking here about well over 1 billion of these devices manufactured each year just for hard disk drives. And what I found very surprising when I looked into this material was that actually no one knew its magnetic structure. So it has 2 types of crystallographic structure, chemically ordered, the L12, which is this one, the L12, the copper-3 gold prototype, and the magnetic structure is known, but this isn't the type of material used in devices. It's this one, the chemically disordered one, the FCC structure. And very interestingly, the structure was not known. There were 3 possible cubic symmetry type structures that were offered, called Q1, Q2, Q3 in these papers, where probably it would be Q3. And I just found it interesting that it's a material very widely used because of its magnetic properties, yet the actual magnetic structure is not known. So this is a case, just very briefly, that we used neutron scattering in order to determine its structure. And we found for this chemically disordered FCC case that the moments are tilted by 45 degrees from crystal diagonals towards cube faces. And actually, it doesn't fit the theoretical predictions for bulk. And the reason we think this is happening is because if you look at these calculations in the literature, this will be the energy as a function of the tilting of the magnetic moments with these 3 predicted structures. And the preference was for this 3Q type structure. And this is where we are. So in terms of the minimum energy, it's quite flat here. And we determined that there's tensile strain in these thin films. So we think that tensile strain is enough in order to change the energetic preference to this kind of structure. But anyway, this is the structure that you actually have in the devices. So I'll just conclude here, and I just wanted to give 2 examples, or rather I focused on one example where electron microscopy is quite crucial, I think, in determining the actual structure of devices at the atomic scale in order to learn about their operation. Okay, so I'll thank you for your time. And, so are there any questions?
So you talk about epitaxial structures.
Mm-hmm.
And how good is the epitaxy in terms of maybe rotation?
Okay, so
have you done X-ray rocking curves?
yeah, that's one of the parameters that is characterized. I don't know. In this case, for example, the mosaic spread is under 2 degrees, and the chemical ordering is around 0.9.
So 2 degrees is good enough, then, you think?
For this kind of research, yeah.
Well, no, I mean for your properties.
Well, this is a model system. What you have in actual devices is sputter deposition.
Probably, right?
There it's much worse. There you have a 1-1-1 preferential orientation. I'm talking about this material. And in plane, there's a much larger spread or even random. And we have work on that which shows that this type of structure, this random orientation, leads to this very peculiar micromagnetic structure. So this is a Lorentz TEM image, and basically the contrast you see here is due to domain walls. And each of these lines, the contrast, is a 180-degree domain wall. So overall, what you see here are 360-degree domain walls, which is actually rather strange if you think about it. The magnetic moment just does a full loop and goes back to its original configuration. And these are very stable structures. They exist also in devices. They've also been seen in devices. Very difficult to get rid of, rather stable. And the reason for them, and we've modeled that in a paper, in 2 papers actually. So it comes directly due to the phenomena you were speaking about this in-plane random orientation of the grains.
Yeah. Can I look at the areal fraction of the 2 different areas and say something about it, or is that not fair?
For this material?
So if I look at that, it looks like it's 80% one orientation and then 20% another orientation.
But you're talking about this result?
Yeah.
So this is a Lorentz result. What you see here is a magnetic contrast.
Okay.
What you're seeing?
2 different areas. It looks like
this and this?
areas, right? No, well.
This is one image. Yeah, this is one image out of many.
Yeah.
There's a whole range of these structures, from rather small to larger one. We did statistics of.
The question is area-wise. I mean, what percentage of the area is occupied
by these structures?
Yeah.
Okay, I don't quite remember the number, but this is quite typical. It's all over the place.
Well, that looks like 80% of one structure and 20% of the other might be correlating with your polarization.
Yeah, but no, this is for the antiferromagnet. I just jumped. This is related to iridium manganese 3. Maybe I wasn't clear. So, in the case of the Heusler structure, this was done by sputtering. Mm-hmm. And but here too, I mean, it's not quite like MBE, but it's quite good.
It should be going to MBE to get the other level of polarization.
Yeah, absolutely. But
sputtering is quick and dirty, and you got to make a billion of them, I guess.
Yeah, exactly.
But if you're trying to get higher quality, you may want to go to MBE.
Yeah, so that's actually one of the topics I'm hoping to work on in the future with an MBE group. Okay. Yes.
You mentioned the problem of surface states or interface states.
Mm-hmm.
That kills the spin.
It creates a spin flop, reduces.
So how do, maybe I missed that. How do you tackle that?
So the way to try and tackle it is to artificially introduce a manganese layer at the interface. So manganese doesn't create this phenomenon, and there have since been groups, or one group rather, that through actually MBE growth puts in a monolayer of manganese. And
manganese itself does not introduce any. It's also kind of magnetic. No?
Yes, but it doesn't create the spin flip. It doesn't create these interface states. And sure enough, when they did it, these devices, the tunneling magnetoresistance shot up. Actually, there's a good correlation with the theoretical predictions on this issue. Pretty much all the options for this material system have been first calculated and proposed, and then people would attempt it. Okay, thank you. So. Our next